Welcome to This Explainer. Today, we're diving into a really fascinating historical mystery, static electricity, and the absolute mechanical genius it took to finally unlock its mathematical secrets. I mean, think about it. Have you ever wondered how scientists took this invisible, almost trivial thing, like, static cling, and figured out the exact mathematical laws governing it? It literally paved the way for our modern electrical age. So we're going to unpack exactly how that happened and step back in time to witness one of the most elegant experiments in the history of physics.
Okay, so to really appreciate this, let's look at what scientists already knew back in the late 18th century. Basically, their scientific baseline was purely qualitative. They knew for sure that rubbing glass with silk produced an electric charge. They knew that like charges repel and unlike charges attract. It was a super well-documented phenomenon. You'd see it in parlor tricks and early lab demonstrations. But here's the catch. While the rules were clear on the surface, the scientific community was hitting a massive brick wall. They understood the what, but they were completely missing the exact numbers to explain the deeper mechanics of the universe.
So the crucial question became, how does this invisible force actually depend on the amount of charge and the distance between the objects? They could easily observe these pushes and pulls, right? But they desperately they needed to figure out the exact math. Does the force drop off suddenly? Is it a linear relationship? Without knowing that exact mathematical dependency, electricity was just a neat trick. It could never be fully understood, let alone harnessed. They literally needed a way to measure the seemingly unmeasurable. They needed a massive technological breakthrough. Enter physicist Charles-Augustin de Coulomb. To solve this whole thing, he engineered an absolutely beautiful instrument called a torsion balance. If you look at its design, it's brilliant. You've got this incredibly delicate internal suspension system housed inside a physical structure with precise measurement dials on a glass cylinder. It honestly looks like a giant, oversized antique compass, but its purpose was way more profound. It was designed to measure ridiculously tiny forces with unprecedented precision, basically by completely isolating the experiment from any outside interference. Let's actually break down how this works. You've got two small metal spheres, and they're both charged up. One is fixed in place, while the other is suspended on this super thin wire. When they interact, the resulting electric force physically rotates that suspended sphere. It is just a total masterpiece of experimental design. Because they're isolated inside that glass case, safe from even the slightest draft in the room, or even a scientist breathing too heavily near it, the only major force acting on that suspended sphere is the electrostatic push or pull from the fixed one. Boom. The invisible electrical force is instantly translated into physical mechanical motion. Now, what's really, really interesting here is the sheer genius of how he measured it. By tracking the literal angle of the twist in that delicate wire, Coulomb could finally weigh this invisible electrostatic force. The wire's mechanical resistance to twisting basically acted like a microscopic scale. A big twist meant a strong electrical force. Just a tiny little nudge, weak force. Coulomb wasn't just sitting around watching sparks fly anymore. He was literally measuring a mechanical twist to calculate the exact strength of an invisible push. By systematically changing both the charges and the distances, he finally cracked the code and established what we now call Coulomb's law. He discovered that the force is directly proportional to the size of each charge, and here's the kicker, inversely proportional to the square of the distance between them. So, in plain English, if he cut the distance in half, the force didn't just double, it quadrupled. If he doubled the distance, the force dropped to a quarter of its original strength. He proved it wasn't some random or linear thing. It followed a strict geometric rule governing how that force radiated out into space. Let's move on and see how this all builds into the actual math. Here's the elegant equation that came out of all that twisting wire. F represents our electrostatic force. You just multiply your two charges, Q1 and Q2, and divide them by the square of the distance, R squared. But I want you to pay really close attention to that K at the front. That's Coulomb's constant, and it is a staggering 9 billion. Roughly 9 times 10 to the 9th power. Having a constant that absolutely massive reveals a fundamental truth about our universe. The electrostatic force is inherently a very, very strong force, even when the actual amounts of charge you're dealing with are incredibly tiny. Visualizing this formula in action, you can clearly see how two positive charges repel each other with an equal and opposite force that perfectly follows the math we just looked at. Because they're like charges, the force vectors point away from each other. But notice that the magnitude of the force is identical for both of them. Newton's third law still applies flawlessly here. The force pushing one sphere away is exactly as strong as the force pushing the other away, dictated perfectly by the product of their charges divided by that distance squared.
And whether the force is positive or negative, whether it's pushing apart or pulling a positive charge and a negative charge together, that inverse square relationship perfectly dictates the strength of the pull. As that distance gets smaller and smaller, the attractive force between them absolutely skyrockets exponentially. It's this highly predictable dance, governed strictly by Coulomb's rules. And it's exactly what allows modern engineers and physicists to calculate precisely how particles are going to behave when they get close to one another.
But here is, without a doubt, the most mind-blowing takeaway from all of this. If you take a step back and compare electrostatic force to Newton's law of universal gravitation, you realize something wild. Despite one acting on microscopic charges and the other acting on literally massive planets, they both follow the exact same inverse square law. Just think about that for a second. Gravity depends on mass and only ever pulls things together. Electrostatic force depends on charge and can pull together or push apart. Yet the mathematical equations governing them are practically identical. Nature is essentially using the exact same geometric blueprint to organize planetary orbits as it uses to bind atomic particles together.
Finding this deep, really striking mathematical symmetry between the atomic world and the entire cosmos leaves us with a thrilling final thought. What other hidden structural symmetries are just waiting to be discovered out there in our universe? Coulomb didn't just solve a neat little electrostatic mystery with some wire and glass. He actually pulled back the curtain on the underlying architecture of reality itself. Thank you so much for joining me on this explainer, and I really hope it changes the way you look at the invisible forces shaping the world around you.